All right, so we did our lab. So obviously you're going to draw me a really cool picture, and if you're not here in the class, it's a lab that you can do at home because all you need is some tape and a comb, maybe some aluminum foil. Should have all that at home. So when you're sticking the tape to the table, you're picking up a charge. So you are going to pick up some negative charge from the table. Obviously the counter worked a little bit better. So if you pick up a tape and you have a negative charge on there, and you pick up have the other tape has a negative charge, when you put those negative charges together, they should do what? Repel, right? Because like charges repel and opposite charges attract. So then when you're combing your hair, and when you're combing your hair, you're going to get, again, a negative charge on your comb from your hair. And then you have some foil pieces that are on the table, and they're neutral, just sitting there. But they do have positive and negative charges, and the positive charges can be attracted to the negative charges that are on your comb. So they're neutral, but it's the positive charges that attract because opposite charges attract. Okay, so.
When we write our lab, do we just write what happened with your pieces of tape?
I mean, I would. You could say my pieces of tape didn't repel and tell me why then, and then probably say what you should have seen or what you saw on another piece of tape, or pretend that you didn't see yours and see mine. I don't care how you do it. So make sure you write a description, but the conclusion is really draw me a cool picture. Obviously yours is better than mine. And then, again, the conclusion is the important part. Make sure you mention about charges. Make sure you tell me, that like charges repel and that opposite charges attract. You'll need to know that for your test. Okay. All right, so you're going to write up a lab for not next week, because we're not meeting next week, but the following week. And then use this time to get caught up. The goal is to send out midterm for all of you, give your parents your grades, and let you know if you're missing anything. Again, I'm famous for grading stuff, not recording it, so I think you're missing it, but it's not missing. You did it, you have a grade on it. Just bring that back and I'll record your grade. So don't meet next week, then the following week we'll finish this chapter, and then you'll have a test on chapter 7 after that. All right, so this chapter, split personality. So parts of an atom. On page 204, it talks about how like charges repel and opposite charges attract. Every substance has an electrical charge, everything, but usually it's neutral. So you have the same amount of positive charges as you have negative charges, but like on the tape that when we ripped up tape off of the counter or the table, you're taking away the negative charges. So that's what leaves an overcharge. Or if it's dry and you're walking through the room with your slippers and then you touch your brother and it zaps them, that's a cool way to find out about charges too. All right. So if a substance, if it has the same amount of positive and negative charges, it has no overall charges, but if there's more of one than the other, then it can take on that charge. And we're going to talk about that with atoms, because the way ionic bonds stick together is one steals the charge from the other. So something has a positive charge then and something has a negative charge, and that's how they stick together. So that's why we know that ionic things only join together one way, and we don't have to add the prefixes to them when we name them, if you remember back a couple chapters. Okay, so on our periodic table, again, handy dandy periodic table, let's see if I can find that. Again, we talked about a number of the numbers on here and the letters on here. Again, the letters are just abbreviations for the names. The numbers on the bottom, remember those are AMUs, but who cares? What we care about is that's how many grams are in 1 mole if you weigh that. When I have the right amount of them, right? If I have a mole of them, it'll weigh that amount in grams. So we didn't talk about the numbers on the top. So they're all consecutive, 1, 2, 3, 4, 5, 6. And there's a different shape to the reason that this is a certain shape is because of the atoms, the configuration of the atoms. But the numbers on the top is called the atomic number, and that tells you how many protons are in your atom. So atoms, maybe you don't remember, an atom has protons, it has neutrons, it has electrons. So again, the number on the top is how many protons are in. So hydrogen has 1 proton. If it's neutral, it will also have the same amount of negative charges. Proton's positive, pro meaning positive, and the electron is negatively charged. So if it's a neutral atom, it will have the same amount of protons as electrons. So kind of, you can say that tells you the number of electrons too, but only if it's a neutral element. So hydrogen will have 1 proton and 1 electron. Now the only way you can determine how many neutrons it has is if they give you the weight of it. And we'll figure that out too. So all atoms have an equal number of electrons and protons. So how many protons, this is the on your own question, and chromium, if you can find chromium, I don't know what number that is. Where's chromium? I don't know, where is it?
24.
24. So how many protons are in chromium? It's not a trick question.
24.
24! So how many, if it's a neutral element, how many electrons are in chromium? 24. Easy. So find whatever you're looking for in here, see that number that's on the top, and that's how many protons are there. Okay? All right. Example 7.1. What's the name and symbol of an atom which is made up of 10 protons, 10 electrons, and 11 neutrons? Okay, so I told you that the number on the top of the box tells you how many protons there are. And if it's neutral, that'll be how many electrons there are. But neutrons, you can only figure out if you have a weight. So this one just says, if you have, on page 207, if you can do the mass number in 2 ways. So you have the 6 protons. I should have reviewed this. Okay. So you add the protons and the neutrons to get the mass number. So if we find the atom that has 10 protons, which number is it going to be? If it has 10 protons, it's going to be number 10. So we find number 10, which is that? Do you know what that is?
Neon.
Neon. Okay, so if it has 10 protons and 10 electrons, that just means it's a neutral element. And then, so you take the protons plus the neutrons, and then when you write it, it's going to be neon, and then you can either write, you add, if it said 10 protons and 11 neutrons, you can either write neon and then do a little hyphen, and 11 and 10 is 21, because this is your protons and your neutrons. You add them together, and it will be isotope number 21. You can write it like that, or you can write neon with a little 21 up here. You don't want it down here, because that's like if you have, you're in your balanced equation, that tells you how many neons you have. You don't want a big number here, because that means I have 21 moles of neon. So it's a little superscript that's before it. Or a hyphen, when you spell it out, a hyphen after it. Okay, so that would be a big number. So if you want to write a superscript there, what does that mean? That means it's isotope number 21. That means I know how many protons and neutrons I have. So protons and neutrons add together to give you that number. All right, so how many protons, electrons, and neutrons make up 129, atom. Now I have to find I on here. That's iodine. And it's, anybody find it?
53.
53. So how many protons do I have?
53.
53. How many electrons do I have?
33.
53. If they don't say that there's a charge on it, you can assume that the protons and electrons are the same. So how many neutrons do I have? Well, that would be my total then. Neutrons and protons together make my 129. And if I know that there's 53 protons, I would have to subtract then. 129 minus 53. So how many neutrons do I have? Can you subtract upside down? I don't know. So there's 76 neutrons then. Okay?
So you don't add the electrons?
Ignore the electrons. So the electrons are going to be helping you with the charge. So electrons are actually kind of what we can see when we're doing the experiments that we did. We saw the results of the electrons when you're zapping your brother with your finger when you have to slide around. That's your electrons that you're zapping it with. Okay, but the number on here is protons. The only way to figure out your neutrons is if they give you this mass number, or sometimes called the isotope number. So, and carbon can have, most things have different isotopes, right? You've done carbon-14 dating probably in biology, you talked about carbon-14. That's your isotope number. But there's a carbon-15, there's a carbon-13, so it's just a different weight of it based on the neutrons. But carbon is always going to have 6 protons and 6 electrons if it's a neutral element. Okay. All right, so they are going to give you examples of elements, and they'll give you the isotope number, and then they'll have you figure out how many protons, neutrons, and electrons in them. Okay, so now we switch to a number of a little bit of history. So I'm not a super huge fan of history. I appreciate history. I appreciate that there's a lot of scientists who had a lot more time on their hands than I do, and they figured stuff out, and I'm very grateful for that. But there are a few things that you will want to remember about the history of this science, specifically atoms, figuring out atoms, what's in an atom. There was a guy, Crook. He wasn't stealing things, but his name was Crookes, and he put some gas into a tube, kind of looks like a weird shaped light bulb to me, and they hooked a battery to it, so they're putting charge through it, and he was able to make it glow. To me, it's kind of like a light bulb. That's what we do for light bulbs. You screw it in and run a current through it, and it glows. Yay, my room lights up, right? So, but he was kind of the first one to do it, and he was trying to figure out why it glowed, and the positive part of a battery is the cathode, so they sometimes call this a cathode ray tube. But the reason that it lit up, it glowed was because of the electrons. So they figured that out later on. It was the electrons that made it light up. But you're going to want to know about Crookes and his cathode ray tube. So if you remember that has something to do with atoms and specifically electrons, that would be great. Dalton, he took some elements, he figured out that we did this in the atomic theory. Did we do that, or is that this chapter? Dalton said that, elements have, all of the elements of carbon are going to have the same properties of carbon. All elements of oxygen are going to be different than carbon because they have the different amount of protons, neutrons, and electrons, right? So if you have the same amount of protons and electrons as something else, you're all going to be the same element, right? So if you have you're the same element, if you have different amount of protons and electrons, you're gonna be a different element. Neutrons just kinda, you can have one carbon with different amounts of neutrons. So neutrons don't really figure in there. Let's see, what else do you need to know? So they were trying to figure out atoms, what makes up an atom, how is it arranged. And when they first tried to figure out, okay, there's a positive part of an atom, there's a negative part of an atom, they didn't really know about neutrons, and they were thinking that maybe it was like they're English, so maybe it was like plum pudding, which to me is kind of like pudding with raisins in, disgusting, but it's pudding that has plums in, and so they were thinking it was like just a mess, and then the electrons, the negative charges, were kind of just sprinkled out throughout the whole thing. But that's not really how it is. So they were thinking, as they're trying to figure out how is an atom put together, what's the shape of it, where are the positive charges, where are the negative charges. They did different experiments. Here's one where Rutherford shined a light onto some zinc, and they were able to see where the light would flash off, and so they had a beam of particles that were positive charge, and they discovered that these protons that the protons, or the positive part of the cell, is in the middle of the atom, and the negative part of the cell is kind of on the outside of the atom. So again, to me, I'm like, yeah, I'm glad they all figured it out. I would never figure out how they figured it out, but we give Rutherford credit for that. So really, he made this model of the atom then, that the electrons are kind of on the outside and the protons are in the middle. And then Bohr, he was not a Bohr, but Bohr figured out that you can excite an atom and make it jump to a different place, to a higher orbital. So if they can jump in and out of orbitals when they're excited, and when they are excited, they give off light. So that's why when they're sticking a charge to it, like a battery, they could get it to glow. So when it gives off light, it's an excited atom, and the electrons have jumped to a higher orbital. So there are different orbital shapes. They're on page 229. So again, like jumps to a different section of your chapter. It's a really long chapter. So he figured out that not just the protons are in the middle of an atom, but the neutrons are in the middle of an atom too, and the electrons are on the outside, but you can excite them and have them jump to even farther out. And when they're excited, they give off light, and then when they're de-excited, they go back to kind of their original home. Okay? There's different shapes of these orbitals. There's an s orbital that's sort of a circular. There's a p orbital that's kind of like this dumbbell shaped. I'm not going to hold you responsible for the shapes of all the orbitals. There's also a d orbital. Just understand that if you know that your protons and your neutrons are in the middle, and the electrons are more around the outside, they're not just sprinkled out throughout like a plum pudding. And if you know that when they get excited, they give off light, that'll be really things you'll want to remember. Okay, you might want to remember about the cathode ray tube. What if you say that he figured out negative charges or electrons? That would be fine too, but Crookes did figure out the cathode ray tube. Okay. Yay, history. All right, now, like I said, this is kind of like a split personality chapter, because then they start talking about light. Let me find back to, so I figured about an atom, and then they're going to try to figure about light. And even though people have studied light throughout a lot of history, we still don't really understand it. And I think my Bible tells me, John 1:5 says that God is light and in him there's no darkness at all. So we can't really understand God. We can try to talk about him and we understand that he's there. We can see light is here. But as much as we try to study it, even the greatest scientists don't really understand it, because sometimes it acts like a wave and sometimes it acts like a particle. So it doesn't follow any of the, it follows rules, but we can't fully encompass that. So, saying that, now you need to know about some things of it. So, so sometimes light acts like a wave. So what is a wave? So here's a wave. If I go from one, this is called the crest of a wave. The bottom is called a trough. So here's a crest. Here's a trough. Like an animal would eat out of a trough. And the difference between a trough and a crest is going to be your amplitude. Amplitude. So how big your wave is from the bottom to the top is called your amplitude. And the bigger your amplitude, the brighter your light is. So your amplitude tells you the brightness of your light, which I really notice when I'm hanging lights on my Christmas tree and I have a string of lights that's a little old and they look kind of yellow and dim, and then we run out of lights every year, some don't work, and we go to the store and buy some new lights, and then those are like bright, like really bright. So as they are older, the amplitude gets smaller, your color kind of changes, and your amplitude, it makes it not as bright. So bigger amplitude, brighter, smaller amplitude, not as bright. Okay? Now, if you go from a crest to a crest, or a trough to a trough, that is called this little weird Greek letter, and that is your wavelength. Wavelength. And the wavelength of your light is what color it is. So that's where we see your red light, your orange light, your blue light, your green light. When you see a rainbow, that splits white light into all its different colors. The reason you see them is because they're different wavelengths. So water is amazing. It can split light into its different wavelengths. So again, from the bottom to the top of your wavelength is your, from a trough to a crest is your amplitude, that's your brightness. From a crest to a crest or a trough to a trough, that would be the same wavelength. That would be your color. Someone getting that? Yeah, okay. Take care of it. Have Dad take care of it then. All right, so what else do we need to know here? Follow my hands. All right, so how frequent your wave goes, like maybe you've played with a jump rope and you can make your wave go really fast, or you can make your wave go really slow. The length of your wavelength, how fast they go, is your frequency. So if I make my wave go very, very fast, then I have a very short wavelength. If I make my wave go very slow, then it doesn't have a high frequency, it would have a very big wavelength. So there's an inverse proportion to how the frequency, how fast it goes, and to the wavelength, the distance between them. So you might it might help you remember about, if this one's big, then this one's going to be small. If this one's big, this one's going to be small. All right, so there is a relationship between, for light, anyways, oh, sorry, does everybody have that? So frequency equals c, which is the speed of light. Oops, that's a G, not an H. speed of light over my wavelength. Okay? And the speed of light, you don't have to memorize it, they're going to give it to you, but it's 3.0 times 10 to the 8th meters per second. Okay? The trick is that usually they give you the wavelength, again it's this Greek letter, it's kind of like a, I don't know, a 10 to the line down. Maybe a backwards crooked H, I don't know. So usually they give you the wavelength in nanometers or nm. Yeah. So nano just means times 10 to the negative 9th. So it's meters, it's just like we did centimeters before, we did kilometers before. Nano means to the negative 9th. Nano, 9. Okay? So it's small. So, example 7.2 says if we know that frequency equals the speed of light, which is in meters per second, and wavelength, they give it to you in nanometers, but you're going to have to convert it to meters. So you have to make sure you convert it to meters. It's like all this excitement going on in my house. So you have to make sure that that's meters also. Then you have meters on the top, and this is, the second is on the bottom of the top, and then this is on the bottom. So really you have meters over meters second. Well, these are going to cancel out, and what you're left is 1 over second. And sometimes we say it's 1 over second, but we call it something else. We call it a hertz. So a hertz is a 1 over second. Okay? So frequency is usually given in hertz. So you can give it in 1 over second, or you can give it in hertz, either one. So let's do this first problem here, which is example 7.2. A violet light wave has a wavelength of 405 nanometers. What is its frequency? So I want to know frequency, and they gave me the wavelength. Well, this is a constant, so I can substitute in, except that I need this to get into meters. So how I get that into meters is I'm going to times and do meters at the 1 times 10 to the negative 9th meters over 1 nanometer. So my nanometers cancel out. So hopefully you can do that in your calculator. You're gonna times it by 1 times 10 to the negative 9th. And really all you're doing is you're moving it over. So you're gonna get 4.05 times 10 to the negative 7th. If you just move your decimal place here, if you can't do the conversion, just move your decimal place there and change it from a 9 to a 7. Okay, go lay down in your chair. So now I have that in meters. And so for frequency, it's the speed of light, which is 3.0 times 10 to the negative 8th meters per second, over 4.05 times 10 to the negative 7th meters. So my answer is going to be, I have 2 significant digits here and 3 significant digits there, so I can only have 2 in my answer. So I get 7.4 times 10 to the 14th meters, 1 over second. So you can write it 1 over second, or you can write 7.4 times 10 to the 14th hertz, HC. Either way is fine. So, I'm sorry, this is positive 8, not negative 8. I'm wondering why my numbers weren't working out. So, the speed of light is very fast, so it's a very big number. The wavelength of my light is very small. So when you have a very big number divided by a very small number, you add those together, except that this becomes positive then. Okay, math. All right, but if you do it in your calculator, 3.0 times 10 to the 8th divided by 4.05 times 10 to the negative 7th, because you're dividing by a very small number, you end up with a really big number. Okay, so what does that mean? That means the frequency, how fast my wave is going, is very, very fast. Okay?
What does the C stand for?
C is the speed of light. Okay? And again, it's not a number that you're going to have to memorize. It'll be on all of your problems. It'll be on the top of your test. Just know that it's the speed of light. It's a constant, so it doesn't ever change. So the trick is remembering that you got to convert your nanometers to meters and just plop it in. If you know frequency, and this is a given, frequency equals speed of light over the wavelength. Or they may give you the wavelength, they may give you the frequency and want you to calculate the wavelength, which is the next one. A light wave has a frequency now of 4.7 times 10 to the 14th hertz. What is its wavelength? And what's the color? Because the wavelength tells you the color according to the chart. So they have this chart on 219. Oh no, chart on figure 7.8. So the chart is on page 215. So here's my chart. So red light is 700 nanometers, violet light is 400 nanometers, and you have the spectrum in between. Okay? So I wrote in my book, my wavelength of red, if that's got a high wavelength of 700 nanometers, it's going to have a low frequency, because remember they're inversely proportional. When one's big, the other one's small. Opposite, if I have a high frequency and a small wavelength, that's more what violet light is. So again, these are really small numbers, so I have a hard time imagining it in my head. So this is the same formula, but now they gave me my frequency and I want to solve for my wavelength. So if you don't know how to do that, you have to multiply both sides by your wavelength so that these cancel out. That means I'm going to multiply that by my wavelength, and I want to get rid of frequency on this side, so I'm going to divide my frequency on that side, which means I got to divide my frequency on that side. What does that end up being? I go from frequency equals C over wavelength to wavelength equals C over frequency. They're inversely proportional. So if this one's, I can just swap them, but this is mathematically how I do it, right? I'm just rearranging an equation. But they are sometimes going to give you want the frequency, and they'll give you the wavelength. Sometimes they give you the wavelength, they want the frequency. If you can remember that you just swap them, that's great. If you can't remember, figure out how to cancel it out and rearrange it. Okay, so now they're giving us the frequency, and they want us to figure out the wavelength. So wavelength is going to be speed of light over frequency. Again, this is 3.08 times 10 to the, what is that, 15th, 14th, 8th meters per second. Well, they only gave me 3.0 at this one. It is 3.08. All right, 3.0 times 10 to the 8th. And then my frequency is 4.7 times 10 to the 14th hertz, which is 1 over second. I like to write 1 over second just so my units cancel. So when I have a fraction on the top, that makes this second come down here. And when I have a fraction on the bottom, when dividing fractions, don't ask why, you flip the sucker and multiply it, right? So that means this S ends up here. So what does that mean? That just means this S cancels that S out. And I get my wavelength in meters. Anybody lose, did I lose you? I'm just showing you how my units are gonna cancel out. So this one was meter per second, this one is 1/second, so when bring my seconds down and this one up, they cancel each other out. Okay, so now I just have meters in my answer. So 3 times 10 to the 8th divided by 4.7 times 10 to the, is it 14 or negative 14? 14. So I get 6.4 times 10 to the negative 7th. Here's my problem. They asked, and that would be fine if they didn't tell me what units they want me to give it to them in. But they asked me what's the wavelength? Fine. What's also the color? Well, to figure out the color, I have to have it in nanometers because this chart that they gave me is in nanometers. So how do I do that? I will do that. I want my meters to cancel out on the bottom to give me nanometers. That's an M. And so this is 1 times 10 to the negative 9th meters, or I can just remember that it scooches the decimal place over 2 places, so that's the same as 640 nanometers. Okay? So I'm lazy, I would probably just move it in my head. So, if something is 640 nanometers, I flip to the little chart, where would that be? Well, there's not a 640 nanometers, so what's it closest to?
Orange.
It's probably an orange light, so I would say 640 nanometers, orange. Okay? Alright.
How did you know how to rearrange the formula?
How did I rearrange the formula, or how did I know to rearrange the formula?
Like, how did you know where to put what?
Because the original formula is frequency equals C over wavelength. Okay? If they give me this one, but not this one, I want to solve for that. If you like to put all your numbers in first, but I know I gotta have that. This is a 1 over wavelength. I don't want to solve for 1 over wavelength. I want to solve for wavelength. So, again, how do I do that? Is I multiply both sides by wavelength so that that cancels out. I divide both sides by frequency, so that cancels out. So I'm left with wavelength equals speed of light over frequency. I just swap them.
Okay.
So what do you want to know? If the question is, I want to know wavelength, I'm going to use this one. If the question is, I want to know frequency, I'm going to use the original one. Equals C over wavelength. So it's whatever my question, what unknown did they give me? That's what I'm going to solve for. Okay, did I lose anybody then? All right, 15 minutes. So you're going to have to use this equation. So that one, you will have to memorize the equation. You just don't have to memorize the constant, the speed of light constant. Let's see. All right, one more thing. This just reminded you that if you have a big frequency, you're going to have a small wavelength. If you have a big wavelength, you're going to have a small frequency because they're inversely proportional. Okay. Then they gave you this spectrum of different wavelengths of different things. Some things you can't see. You can't see gamma rays or X-rays. We can see this visible spectrum, which is all your colors of red, Roy G. Biv, right? Red, orange, yellow, green, blue, violet. Then there's all these, the light is all this, works sort of all the same. Depending on your wavelength of light, it can do lots of different things, right? Gamma rays, X-rays, radio waves, all of them are just different wavelengths. All right, so there's a relationship also between frequency and energy. If your light wave's frequency is going to increase, its energy also increases. There's a direct relationship, not an inverse relationship where one's bigger and one's small. This is a direct relationship. One's big, the other one's big. Okay? So there's a relationship here of energy equals this Planck's constant. So here's another constant. Again, you will not have to memorize this constant. You just need to know how to use it. They will give it to you, H. It's called Planck's constant. It's from a scientist named Planck. He figured out it helps us to relate energy and frequency. Its value is H equals 6.63 times 10 to the negative 34th. Again, how we figured it out, I have no idea. And it's joules, because energy is in joules, and if I would have done chapter 2, we're going to do a lot of things in joules. It's just a way that you measure energy, okay? So it's joules per hertz. Oh, hertz again. Remember, hertz, you can either write 1 over s, it's 1 over second, or hertz, H, oh, I should spell it. H-E-R-T-Z, not like how it hurts, but this is a scientist named Hertz, and so it's H-Z from his name. Okay, so 1 over second is a hertz. So this Planck's constant is how much energy or joules are in a hertz. So joules per hertz. So it's this Planck's constant H times my frequency. So you would hertz is going to, Planck's constant is going to be joules per hertz, or joules per 1 over second, and that's going to give me my times my frequency, which is going to be in hertz or in 1 over second, right? So these will cancel out when I'm doing these problems, and I'm going to get energy in joules. That's a J. Joules is, I think it's how it's spelled. Okay, so I'm just showing you how your units are going to cancel out on these. Okay, so just so you know, this marries together with the other formula that you are going to memorize. Frequency equals C over wavelength. So you see how they're going to do these problems like an evil way, right? They're going to want you to figure out the energy, but they're not going to give you the frequency. They're going to give you the wavelength, which makes you figure out the frequency, and then you're going to have to use that in this energy one. So you have to memorize both of these formulas. You have to know how to rearrange this, which that's simple. Same thing, okay? So they'll give you the frequency, or the wavelength, and you just have to know that it's the same thing, okay? Okay, so let's do it. I'm going to leave this H up there. Planck's constant. All right, this is example 7.3 on 222. A light wave has a frequency of 2.3 times 10 to the 16th hertz. Not negative. What is its energy? Well, that's easy. Well, that's just energy equals Planck's constant times frequency. It wasn't bad. So we just drop in what we know. So energy equals Planck's constant. They will give that to you on your page in your book, in your question, whatever. Don't memorize it. Negative 34, just know it's a constant, Planck's constant. Joules per hertz. And I'm going to multiply by what my frequency is, which is 2.3 times 10 to the 16th hertz. So as long as you can use your calculator, this hertz is on the top, this hertz is on the bottom. And maybe you write it like that so you can see that it's on the bottom. I don't know. Either way, that's fine. Joules per hertz or joules slash hertz. Just remember this is on the bottom. So this is on the top, this is on the bottom. They cancel out. And so I'm left with energy that's in joules. So you're going to take 6.63 times 10 to the negative 34th. Hopefully you know where your EE button is, or your times 10 to the whatever button is. Times 2.3 times 10 to the positive 16 hertz. And you should get, this has 3 significant digits, this has 2 significant digits. I can only have 2 significant digits. 1.5 times 10 to the negative 17 joules. Okay, does that mean anything to you? I mean, it's energy. It's got a negative 17 there, so it's just a little bit of energy. Okay? So, now they're going to marry the two formulas together. So again, here's our formula. Energy equals Planck's constant times frequency, and frequency equals speed of light over wavelength. I'm going to marry them together. Okay. A light has a wavelength of 1.21 times 10 to the negative 12th meters. Dang it, it's in meters. I gotta convert it. What is its energy? All right. So, oh, actually, I don't need to convert it. Because light, remember my C equals 3.0 times 10 to the negative 8th, no, positive 8th meters. So it's already in meters. Yay. I was thinking I had to convert it. Okay, so what's my question? What's its energy? So I want this, but I have this. So I have to first use this equation to figure out my frequency. And then I'm going to plop that in there. And then I'm going to use this equation to figure out my energy. Okay? A lot of math. So frequency equals 3.0 times 10 to the 8th meters, that's C, divided by what they told me my wavelength was, 1.21 times 10 to the negative 12 meters. My meters cancel out, yay, I'm happy. And my frequency gets to be 2.5 times 10 to the 20th, well, this is meters per second, dang it. 1/second, or hertz, either one. So if you want to write 1/second, that's fine. If you want to remember that it's hertz, that's fine too. Which you might, because this is given to you in joules per hertz. So just remember they're interchangeable. Now that we have a frequency, I can put it into this equation because I want to know the energy. Energy equals Planck's constant, 6.63 times 10 to the negative 34 joules per hertz. And I'm going to multiply that by my answer here, which is 2.5 times 10 to the 20th hertz. This hertz cancels this hertz out, and I'm left with energy that's in joules. So 1.7 times 10 to the negative 13 joules. Again, just a small amount of energy. But a small amount of energy can make a big difference. So, all right. Anybody have a question? So what's important about this chapter? Yay! If you like this, you'll love physics. This is great. This, to me, is more physics than it is chemistry. What we were doing last week with stoichiometric coefficients, balancing equations, mixing things together, that to me is chemistry. This is understanding how the atoms work. Atoms make up light. Light sometimes works as a wave. These are how to figure out wavelength, frequency. Exciting. Again, if you like this, you're going to be on board for physics next year. So memorize this equation. Make sure you know how to flip it. If they give you frequency and you want it a wavelength, just make sure you can flip that around. And then make sure you memorize energy equals this Planck's constant. Again, just know what it is. You don't have to memorize it. And this is usually where you're going to get this frequency. Okay? Remember that the cathode ray is what Crook figured out for electrons. And we'll talk more about electron configuration after Thanksgiving. Okay, good.